Okay. So we're going to resume where we were yesterday. Okay, and I'm going to try sort of a multimedia presentation here because these boards are a little difficult and hard to see. Every time I go back, I see if you're not sitting in row 3, you clearly can't be paying any attention at all because it's all invisible. I will try and talk with appropriate slides up, and hopefully you'll stay awake and catch all the additional typos. But we have a number of things I'd like to cover today. I'd like to just remind you where we were. So we had learned about the basic structure of n equals 1 supersymmetric field theories. We'll apply this, I hope, either today or beginning of the lecture on a Sunday to some of the things you've been hearing about in the other lectures, n equals 2 and n equals 4. I know some of you are very familiar with some of these things, but some of you are not, and maybe give you a little context, even retrospectively, of Nikita's lectures and some of the other lectures you've heard. But anyway, we talked about a very simple field theory. Let me just remind you, one with a superpotential, which was just lambda phi cubed. Okay, and we had various sorts of interaction terms. We had a Yukawa coupling, and we had a quartic scalar potential. And actually, that should have a, again, if you're catching my typos, that should have a minus sign since I'm writing the Lagrangian, not the Hamiltonian. And this model, we talked about R symmetries, and R symmetries have been implicit, actually, again, in some of the other lectures you've heard, and they're going to be important for us. This model has an R symmetry under which the scalar component of this field rotates by a phase e to the 2i alpha over 3. Remember, the R charge of W has to be 2. So the R charge of phi is 2/3. And psi has R charge, which is, oh my goodness, another typo, which should be 1 less. So that's e to the minus I alpha over 3. W itself transforms with a phase e to the 2i alpha. Oops. Well, that's not good. OK, so so I'll skip this because we talked about this quite a bit, but there's this general statement about R symmetries. We talked a little bit about the radiative corrections to the scalar mess, and we saw that there was a bosonic contribution and a fermionic contribution. These two cancel. These two terms cancel. There was some 4, which is a combinatoric factor, which I'll let you work out. And the minus sign here for the fermions arises from the fermion loop. OK, there's a 2 when you take the trace here, and that gives you, in the end, this factor of an exact cancellation of these two terms. OK, so we have these terms which are quadratically divergent, as we talked in the first lecture, and they cancel. OK, so this we saw yesterday. I'm pushing like frantically here and nothing happens. OK. We also considered adding soft breakings, and this is really where we're going to pick up today. We considered adding soft breaking terms, and the simple term we added here, I at least have the sign right, was a mass for phi, just out of the blue, but in the spirit of this naturalness argument of a 't Hooft, or this naturalness principle, I should say, of a 't Hooft. Where there's in the limit we would restore of m goes to 0, we would restore the supersymmetry. We looked at then delta m phi squared, and we saw that this went like lambda squared m squared over 16 pi squared. There's a minus sign that got dropped here, and a log. Okay, so instead of having, so as m goes to 0, this goes rapidly to 0. Okay, and the divergence is now, like for the electron mass in QED, is just logarithmic. Okay. Eventually, I'm going to realize that this doesn't work, and I'll stop pushing the button. OK, and so more generally, we said that we had certain kinds of possible soft terms. We had scalar masses, we had Gugino masses, we had cubic couplings of the scalars, and all of these have dimension less than 4. They're all soft, okay, in the sense that at high energies, their contributions are die off. Okay, so that's our basic structure. And then we started to talk about a simple generalization of the standard model, which is supersymmetric. So we have here a gauge group SU3 cross SU2 cross U1. We have chiral fields for each fermion of the standard model. We had two Higgs doublets, HU and HD. And the fundamental reason we stress for this, why we need at least two, is we need to cancel anomalies. Otherwise, if we just introduce one partner, if you like, for the doublet of the standard model, we would have anomalies in the U involving the U1 current. Okay. We'd actually also have an SU2, so-called SU2 anomaly, a non-abelian or Witten anomaly. But in some senses, that's non-perturbative. Well, they're all important. In any case, this theory would not make sense without the second doublet. And then we left off yesterday writing a superpotential for the model. Okay, so the superpotential has terms that just generalize the Yukawa couplings of the standard model. You could think of this as the Yukawa couplings in a version of the standard model with two Higgs doublets. Okay, all these preserve SU3, SU2, and U1. Okay, here the way I've written things, these YU and YD are 3×3 matrices in the space of flavors. So these Q and U bar have generation indices 1, 2, 3. Similarly, D bar and E bar and L, which got dropped here. Okay, so there should be an L, HD, E bar. Okay, and these Yukawa couplings are 3×3 matrices in the space of flavors. Okay, so now we've omitted a dangerous set of terms from W. This we started to talk about at the end, which are these terms. We have terms which violate baryon number. This is a delta B equals 1, delta L equals 0. These other terms violate lepton number, delta L equal 1. Yeah, they're all delta L equals 1 or delta L equals -1. Whoops, I don't know what this is. Anyone know what that is? That's another misprint. Yes. Oh, thank you. Mystery solved. Thank you. Yeah, perfect. All right. So I want to talk a little bit then about, so what do we do to get rid of these? Okay, so what's been done traditionally to get rid of these? So these are clearly terrible. Okay, so if we combine, for example, delta B equals 1 and delta L equals 1, we can generate a process P goes to pi plus, let's do a P goes to pi 0 E plus, for example. This is consistent with angular momentum and Lorentz symmetries and electric charge, if I've done it right. And it's allowed if I have operators like this. And if I make a naive estimate, if these Yukawa couplings were order 1, right? So if the Yukawa couplings were order 1, the lifetime of this will be something ridiculous. The lifetime of this will be, even if we think about the breaking of supersymmetry, say at a TeV scale, we might expect this lifetime to be something like 1 over TeV to some power, maybe TeV squared, MP cubed, times some small coupling. Let's put lambda fourth. Okay, but if this coupling were order 1, okay, this number would be of order fractions of a second. Okay, and we know that the lifetime, people know what the lifetime of the limit on the lifetime of the proton? 10 to the 33 years, roughly, right? So we're way off. Okay, and so people, to suppress this, usually just assume that they postulate something they call R parity, a Z2 symmetry under which the quark, lepton, and lepton superfields are even, and HU and HD are odd. Okay, this has the effect of making all the new particles, all the superparticles, odd. Okay, and the known particles even, where the known includes the Higgs. Now, why is that? Now that's kind of funny because I'm now distinguishing. Here in one case I just distinguished the Higgses and the I distinguished the Higgses and the quarks and leptons. Okay, so why do I speak of the fermions and the bosons? Well, I can always combine this symmetry with a rotation by 180 degrees. Okay, so a rotation by 180 degrees, okay, is just multiplication of the state by -1 to the f, right? So a rotation, I'm sorry, 360 degrees, not 180. Okay? So rotation by 360 degrees flips the sign of fermions, okay, and leaves bosons alone. Okay? And so the effect of this is to give the ordinary quarks and leptons, keep the ordinary quarks and leptons even, and make their super partners odd. Okay, so all right, so this suppresses all these dangerous couplings and protects proton decay. I'll argue probably next time, okay, that this might be a little bit overkill. Okay, but for the moment, this has a remarkable consequence that the lightest of the new particles, the LSP as it's called, is odd and it's stable. Okay, and so of course you're going to hear an alternative idea for how dark matter might originate from Eric next week. But for the moment, this is certainly looks like a potential dark matter candidate. And in the spirit of Slava's lectures, we can try and estimate. You're now experts on cosmology. Certainly on the cosmology, you need to do this estimate that I'm about to do. And so we can ask what is the abundance of whatever this particle is? Of this LSP. And we'll have to make some assumptions. We haven't developed much of a theory of this yet, so we'll have to make some assumptions about what's going on. So what I'm going to assume is supersymmetry, the characteristic scale of these new particles is a TeV, and the characteristic scale of their interactions is a TeV. Okay, so let's put sigma, actually I'll put 100G, I'll put mz squared. So I'm going to assume that sigma is of order 1 over mz squared. Okay, this is going to be a really crude estimate. I don't have coupling constants or things like that in here. But if sigma is of order 1 over z squared, okay, and I'm going to, and this is also the mass of the super partners. Okay, then I can ask at what point, the first question I'd ask is at what point do the interactions of these particles drop out of equilibrium? So I'm particularly concerned about things like annihilation and production of these particles. So for example, for annihilation, if this LSP is some new neutral particle, maybe the partner of the photon, the photino. Okay? So if I have something like chi, I have some process by which they annihilate and produce ordinary particles, maybe photons. Okay? So the cross-section, I'm assuming, goes as 1 over z squared. The rate for this process goes like, put it here, gamma goes like n chi squared, the density, times sigma. Okay, that has, so this is the, have it right? Yes. N chi, yes. Okay, so, and we want to ask, when is this comparable to the expansion rate? Actually, I'm sorry, I want n chi. So this is, so if I imagine this chi rattling around in the universe, and scattering off, finding its friend, okay, I can ask how quickly does it decay? This is the right dimensions, okay? And so I want to ask, when is this comparable to the expansion rate? The expansion rate goes as t to the 4th over t squared, excuse me, this you learned from Slava, over m Planck. Okay, so it goes like the temperature squared divided by m Planck. Okay, and so I want these two things comparable. Okay, so this is going to translate into a relation that n chi goes as t squared over mp. okay, times 1 over, you're going to want to make sure I got my dimensions right, 1 over sigma. Okay? Okay. And if I now assume, okay, so now let's suppose when is this going to occur? What's going to occur for when the temperature is around this mass, maybe a little bit, an order of magnitude or so below. Okay? So I can estimate n chi, okay, from this. So sigma is of order mz squared, t squared is of order mz squared, roughly. And so m chi, in fact, let me estimate n chi over t cubed. N chi over t cubed is of order mz over mp. Okay? So I can estimate the density. Okay, and then I can ask, I can do what Slava did. I can ask if this is the density initially. So initially the density, the fractional density is small, okay, and the fraction of the energy density is small. Okay, but if I now ask how does the system evolve, okay, the system evolves. Remember what Slava taught you is that that matter, the density of matter over n radiation goes like 1 over the temperature. So as the temperature drops, the matter comes to dominate. Okay, and I'll leave you as a little exercise to work out that when the temperature is of order an electron volt, so all this is really crude. What happens I think Salaba told you, when the temperature is of order an electron volt, that's around the time that matter and radiation should be in equal proportion. Okay, so matter should come to dominate the energy density. And you'll find that roughly, okay, you just do this simple-minded estimate, okay, that roughly the energy density at 1 eV in this dark matter is of order the energy density in radiation. Okay, and that's what we want. That's what you'd like. In fact, if the whole picture of dark matter is to work, exactly that time, at exactly this time of order an electron volt, okay, matter and energy must be comparable. Now this is really crude, obviously, okay, and people do much better. People do fancy Boltzmann calculation, Boltzmann calculations, and compute the rates carefully, compute the cross sections carefully, and you'll see, and maybe even you'll see in some of Maria's talks slides, you'll see figures of how what ranges of masses are compatible with limits from LHC at the moment, and so on. But you can just convince yourself in a rough way that this is really a very promising setting, okay, for understanding the dark matter. Okay, and it's one of the very appealing features in general of supersymmetry. Now, that said, let's go back and let's think about these soft breakings. So let's ask, what sorts of soft breakings can we add in the MSSM? Okay. So we know what we're allowed to add. We're allowed to add mass terms. Okay, so we're allowed to add, for example, Q star. These are the doublets, QF. Let me put the indices on explicitly. M squared Q, FF prime, QF prime. Okay, so mass terms for the Qs. Okay, we can add mass terms for the U bars. Okay, and so on. Okay, so for the D bars, and for the E bars. Let me write it like this. Okay, so this is one set of parameters, and at the level of adding these soft parameters, soft breakings, okay, at the level just this Tuftian kind of naturalness, we can add. These things are arbitrary. We can add whatever we want. Okay, and so let's in fact count. Okay, so these are 3 by 3 Hermitian matrices. Okay, so how many? So I have to count on my fingers. I also have to not lose this eraser. So let's count. I want to sort of figure out how many parameters there are here. Okay, so we have So we have three 3x3 Hermitian matrices. A 3x3 Hermitian matrix, right, has 3 entries on the diagonal, and 1, 2, 3, so 6, 9. Okay, so there are 9 entries. So we have 9 parameters. So I'm going to put number of parameters. Okay, so I'm going to put these m squareds. Okay, and we have 9, and we have a matrix like this, an m squared matrix like this for the u bars, the d bars, and the e bars. Okay, so that's 9 times 3 times 3. Okay, or oops, am I counting right? U bar, q, u bar, d bar, l. That's 3. I'm worried I'm going to get actually, I'm just going to skip ahead here and make sure I don't make a mistake. So am I leaving anything out? So I have q, u bar, d bar. I'm sorry, l and e bar. That's right, 4. Okay, so 4 times 9. Which is 36. Okay. And so I've got it here, so let's just do it from here. We have cubic couplings of the scalars. So these are allowed. So we have q, hu, u bar. Okay. Q, h, d, a, d bar. And each of these are 3x3 complex matrices. Okay. Otherwise unrestricted. So there are 9 parameters in each of these matrices. Okay. So we have 9, 9, 9. So that's another. I'm worried I'm counting wrong. Q, A, U, U bar, Q, A, D, D bar. Yeah, that's all of them. H, D, L, E bar. So it's 8, I'm sorry, so it's 18, excuse me, 18 times 3. So we have 54. Okay, I don't even have the excuse of jet lag. I should be able to count now. Okay, then we have masses for the gauginos. Okay, the masses for the gauginos are complex numbers. Okay, if we think about in 2-component fermions, there are 2 parameters for each. There's a magnitude and a phase. We have 3 gauginos, so that's 6. Okay, so we have already a lot of parameters here. Okay, then we have also we have the parameters in the Higgs sector. So we have this mu. I'm going to count that. This mu that we put in the superpotential. That's 2 more, because that's another complex number. And we have b mu. B mu is the coefficient. If I've got it here, let's see if I've got it here, of hu, hd. Yes, there it is. Okay, so we have this parameter here, hu, hd. So that's 2. And we have the masses of these masses for hu and hd. Okay, those are real numbers. That's another 2. Okay. So if we add this together, I hope I've got it right. I have 36 and 54, which is 96 plus 6, so it's 112. I feel like I've got 1 too many. Let's see. Yeah, I'm missing. I've got mu 4, 54. Oh, it's because I'm sorry, it's because I did this one. 3x3 Hermitian, yes, this is 45, sorry. Okay, so this total is 111. So we have 111 new parameters. Okay, so if supersymmetry is discovered in the next year or 2 or 3, okay, we'll be dealing with a system which has at least 111 new parameters, but not really, not quite. Okay, so I've overcounted just a little bit. And why? Well, first of all, the standard model itself has 2 parameters in the Higgs sector. Okay, and the theory, if I leave out mu here, and I leave out these other terms, okay, without mu and without the soft breakings, the MSSM has certain symmetries. So if I go back and look at this, the Lagrangian I had here, This Lagrangian has certain symmetries. It has an R symmetry under which all fields have charge 2/3. Okay, and it has a symmetry which people usually call the Paget-Quinn symmetry, under which I rotate HU and HD by the same phase. And I rotate the other superfields appropriately. So this is just an ordinary symmetry. So actually it's two symmetries, and both these symmetries are broken by the terms I add, these very soft terms. So the mu term breaks this symmetry, for example. Okay? And the gaugino masses break the R symmetry. Okay? So that means I can use the original symmetry I have, these original symmetries, to redefine two of the phases in the theory. So I get to subtract the two parameters in the Higgs sector, and I get to subtract the two from symmetries. Okay, but there's actually one more set of symmetries, and these are lepton number symmetries. So if I look over here, okay, where I have the L missing, so if I should have L, H, D, E bar, okay, then I have a separate lepton number symmetry for each flavor of lepton. Okay, and you can ask me later what happens when I have neutrino masses. Okay, but I have three separate symmetries. One of these is preserved even by all these things I've added. So there's an overall lepton number which I at the moment have preserved. Okay, but the separate lepton numbers I violated. So that's two more. So I get actually this 2 becomes a 4. Okay, so from my 111 I subtract 6. So altogether I have 105. Okay, 105 new parameters. Okay, so that's when I talk to my experimental colleagues, that sometimes they get annoyed and they say, well, gee, we discover supersymmetry and we already have all these parameters we don't understand, and now you give us 105 more. Okay, and that's true. That's an issue here which we want to think about. We want to think hard about. Okay, so we have 105 new parameters here. Okay, so let's go back here. Yeah. Okay, so this is this counting here, summarized here. Okay, well, I've already talked about dark matter. Okay, I'm going to talk about these parameters in a minute, but let me talk about one more feature of this theory, which is unification. Okay, so let me go back, in fact, to this first point. So, in some ways, saying I have to impose this R parity, we could argue that's kind of disgusting. And a lot of people in the early days, and even now, when they think about supersymmetry, say, well, this need to impose this R parity is one of the reasons not to believe in it. And maybe that's right. Okay? But this bonus of dark matter is really appealing. In fact, I'm going to argue it's seductive and almost too seductive, okay, as we go along. But another bonus is coupling constant unification. And you've all heard about this. And if you have never done the exercise, you should go home and do it. Okay, so let me just tell you what you have to do to study unification of coupling. Okay? So I don't know in what form you've learned or you like to write the solutions of the renormalization group equations for a gauge theory, but I like to write them in the following way. I like to write them in terms of G, and to write 8 pi squared over G squared at some scale mu is equal to 8 pi squared over G squared at some scale lambda plus B naught, the lowest order coefficient of the beta function, times log of mu over lambda. Okay, so that's the lowest order solution. The next order solution, by the way, we'll want actually later. So let me just write it, but well, you could use it if you want to really work a little harder. It involves the next term in the beta function, B1 over B naught, plus times log of G of lambda over G of mu. And I think I've got the coefficient right here. Let's see, actually, yes, I think it's written correctly here. Okay? And then there are further corrections which are, okay, and this clearly sort of implicitly defines how G runs. Okay, usually most people, most of the time just keep these first two terms, and for the moment, for my discussion, I'll consider that only. Okay, so what's the idea in unification? The idea in unification is we have our three couplings, the couplings for SU3, SU2, and U1, so I'll put an A here just to indicate the difference. Okay, so there's some beta function for SU3, SU2, and U1. Okay, and if we hypothesize that there's some unification of couplings, what we can do is we can take this lambda to be some unification scale. I'll call that M gut. Okay, we can compute these B naughts. So the B naughts follow from a formula which you can also work out straightforwardly. This is 3 times the quadratic Casimir in the adjoint minus sum over these chiral fields and phi times the appropriate Casimirs. Okay, let's see. I want a half here, I guess. Okay, so there's some formula that you can work out pretty easily. You can just work it out from Peskin and Schroeder. You can look it up. Okay, and you just plug in. Okay, so basically, what would you plug in? You'd plug in, for example, these are 3 linear equations. Okay, you can think of these as 3 linear equations which determine this log on the couplings, and you can say start with the known values of the SU2 and U1 couplings at MZ. Okay, and solve for the log and solve for the SU3 gauge coupling. Okay, and so if you like, you can view this as a prediction of both a scale and a coupling constant. And, whoops. Okay. And if you do this in just the standard model, okay, without supersymmetry, okay, you find that the couplings don't meet. Okay, the unification the width of the lines here indicates the known errors in the couplings, and and so things don't meet within the errors, not even close. Okay, if you assume supersymmetry, and so what I mean by that is I assume that there are all these additional states, these squarks and sleptons and so on, at a scale of order a TeV, then the couplings in fact meet. They meet at a scale which is about 2 times 10 to the 16th GeV. Okay, and you can think of this as being a prediction of the SU3 coupling given the U1 and SU2 couplings. Okay, so these are sort of the two.
This computation is assuming that there is no more matter.
Absolutely, it assumes what's so-called desert, right? So it's a very strong assumption. The output is one number. Okay, so you can view it. So depending who you are, you view this as a triumph, or you view this as, oh, what's the big deal? Okay, so if you're Savas Demopoulos, you view this as a triumph, and if you talk to other people, there may be a little more. It's one number. Okay, at the moment, we don't have a lot to hang our hats on here, so there are just these two things.
What is the assumption?
That the assumption we've made here is that there are no new particles, in between the TeV and 10 to the 16th GeV. Or if there are, I should kind of modify it a little bit, or if they are, they're in complete SU5 multiplets. Okay, what does that mean? Why do I say that? That's because if I look at these couplings, okay, if fields lie in SU5 multiplets, then what I mean by that is each field makes the same contribution. The change in the beta function at the new threshold is the same for each coupling. Okay, and so as a result, this computation at one loop at least is unaffected. Okay, it's unchanged.
These 3 lines meet exactly, or they meet to some?
They meet to some precision, which you can sort of see in the picture. And you can debate a little bit about how perfect this is or isn't, but it's pretty good. So, for example, threshold effects up here will alter this. So what exactly the microscopic theories? Is it string theory? Is it a theory based in SU5 or O10? Okay, that will affect a little bit this endpoint here. So you can't beyond some accuracy, this kind of computation isn't meaningful without a more detailed microscopic picture.
So would this still be true if the scale of supersymmetry is higher?
It gets worse as, I unfortunately don't have a plot here, but it will get worse as you push the scale up. I should say also that those of you who are aficionados of things like split supersymmetry, and this may again come up in some of the talks, maybe in Maria's talk, that this computation is driven largely by the gauginos and the Higgs. Okay, so there's the refinement of your question is if what moves? If everything moves up, it gets poorer. But if you, for example, just move the scalars up, this calculation still does reasonably well. Okay.
And if you put in right-handed neutrinos for the seesaw mechanism, can you?
Well, the question is, well, the right-handed neutrinos are sterile or neutral under these interactions, so that doesn't change things. And also, the usual assumption is that they're heavy. So if they're at, say, 10 to the 14th GeV or something, even in higher loop corrections, they're not going to affect things. But no matter what, they're going to be small. They're going to be small corrections. So I sort of left them out of my counting down here. In fact, if I wanted to count parameters, I was thinking of a question that David asked me, and he's not here now, but said, well, what about neutrino masses? Well, neutrino masses, from the point of view of low-energy physics, we can presumably represent in the standard model by dimension 5 operators. This operator which, so let me write it in terms of Higgs. So some Higgs, LL. So H, let me write it like this, HL. Within the standard model, HL, HL. Okay, so this is a dimension, let's see, am I writing this correctly? Yes, this is a dimension 5 operator. Okay, this is a dimension 5 operator, so it has some coefficient of order 1 over some mass scale. Okay, so in the seesaw mechanism, that mass scale is the mass of the right-handed neutrino times some coupling constants. And at low energies, we could represent the effective Higgs this way. And then what do we add? So if we think of this as a part of the standard model in some loose sense, then we would add in the MSSM, we would add in particular an analog of this A term, something where we have for example, 4 scalars. Okay, so we would have things with 4 scalars, 1 over m, and some A, and some, I'll put H twiddle, L twiddle, H twiddle, L twiddle. Okay, and we should be so fortunate as someday to be able to measure something like that. So I'm not going to sort of worry about that in my counting. Okay, so it's some non-renormalizable operator, which we, I say we should be so fortunate. You should be so fortunate, certainly not in my lifetime. You should be so fortunate in your lifetimes that we would be able to look at such a thing. Okay, so these are these two sort of things that are not. To glorify them as experimental predictions or outputs is perhaps a little much, but 2 of the things that have given a lot of the energy or a lot of the traction, if you like, for thinking about supersymmetry over these last number of years. Okay, so let me say a few words about these soft parameters. So these soft parameters are highly constrained. Okay, so they're constrained by a variety of things. They're constrained, as we'll hear from Maria, they're constrained by LHC searches. And let me see if I can have at least one figure. Didn't come out that well here. But they're constrained from LHC searches at a rough level. If you assume all the masses are comparable, the gaugino and squark masses are comparable, and there are no hierarchies among them, and so on, then roughly speaking, they're constrained right now all to be about a TeV. And we'll see actually that a TeV is troubling, okay, in a few minutes.
The results that we've seen so far said anything that ruled out possibly the MSM, or is that premature to say?
Depending how much tuning you're willing to tolerate, you can never rule out the MSSM. So there's a matter of, there's a sort of question of, yeah, I think that's a safe, I think what I said is a safe statement. I don't think you can rule it out if you're willing. So we'll talk about it in a few minutes, and you can decide whether the MSSM, as you hear from here today and hear Maria's lecture, whether so you heard the that Maria argued will tell you that it's not. I'm personally pretty worried. When I gave a talk a couple weeks ago at a conference at SLAC on LHC physics, just before the announcement of the Higgs, when the air was full of rumors, I was I expressed a rather pessimistic view, but I also had found that morning when I gave the talk a quote from John Ellis in The Guardian saying, well, if the Higgs is 125 GeV for supersymmetry, that's fine and dandy. So I tried to sort of hinge some level of optimism on that. So no, we can't really rule it out. And I'm also going to talk about extensions. And let me just maybe to say, because I don't know how much time I'll really have, let me say that there are two kinds of situations where we might improve this. Well, maybe I'll say this in a few minutes. But where we might improve on the MSSM. One where we add additional singlets, and Maria alluded to that yesterday. And another is where we give up this R parity violation, this R parity assumption. Okay. Now I'm afraid I'm a little bit of a pessimist in the way I've referred to, especially the giving up R parity is a little bit like you're on a boat that's sinking and you start throwing out things that have excess weight, so I would say that there are it's not. I like to look out at all of you who are not invested in any of the set of ideas we have around now, and hope that one of you will say the correct way to think about some of these problems is such and such. Maybe from Eric we're going to have clues. Maybe from some other totally different framework. But these ideas are certainly under some, in my view, under some tension, and I'm going to explain that in just a few minutes. Okay. So let me talk a little bit about the constraints then on these soft breaking. So one is just this overall scale of kind of a TeV. As I say, when these plots are made, these plots you see are all made with some assumptions about what the underlying model is. And one of the things you certainly want to do is look at those assumptions and ask what things you might give up, what things you don't think are that well motivated. But there are other constraints that we had even before anybody did any kind of experimental search for supersymmetry. And these come from processes that involve flavor. Okay, and this really means things that distinguish the different flavors of quarks. Okay, so a very famous calculation in the standard model is the calculation of the mixing of K0 to K0 bar. How many of you are familiar with this? Is like a few of you. Okay, it's sort of like, actually I could have asked the same question about conformal field theory and string theory and so on. Even people were remarking in the hall about how in string theory there's so much to learn, and the things that people sort of learned 20 years ago, they don't learn so well now. Similarly with lots of things in particle physics. But this is a very interesting system, and I really would recommend you go home and read about it. But the mixing of K0 and K0 bar arises. So first of all, this system is interesting. It's the first system in which people discovered CP violation, and it has all sorts of beautiful quantum mechanics. Okay, you produce. You ask what are the energy eigenstates, what are the flavor eigenstates or the weak eigenstates, what do you produce, you see all kinds of mixing. So anyway, but how does this mixing arise? The mixing is very small, and it arises in the standard model from processes like this. So the K0 is something, I always forget which is the K0 and which is the K0 bar, but you have something like S d bar. Okay. And I can draw, for example, a diagram like this where I have a W plus and a W minus. And I have, over here, I have something like B bar S. Okay. So I have something here where I have a K0, and it goes to a K0 bar. Okay. And your naive assumption is that, or your naive guess, if you didn't do this computation, would be that, well, what's the rate? So you write some rate, and you'd say, well, this should go like 1 over mw squared, and there's a g squared for SU2. Okay, and then you'd say there's a g squared over 16 pi squared. And then to make up the rest of the dimension, this is w squared squared. I'm sorry. No, I'm sorry. I'm going to leave it like this. Okay, and then to make up for the rest of the dimensions, I would put something like mk cubed. Okay. And if you took that as your estimate, you would be wrong, wildly wrong. You would be wrong by a factor of order 10 to the minus 5. Okay, so this is a lot like these hierarchy arguments I gave in the beginning. Okay, and you say, well, why does this, what happens? Well, the explanation of this is that the actual rate is much smaller. In the limit that you neglect the quark masses, okay, flavor is actually conserved. Okay, so I talked a little bit about the symmetries of the standard model in that limit. There's some SU3 cross SU3, and that symmetry is enough to prevent this sort of mixing. Okay, and the result actually you get here involves things like MC squared times some Cabibbo angle, or I should say it's suppressed by MC squared over MW squared. So that's this number of order 10 to the minus 4 or 10 to the minus 5. Or MT squared times, I forget, VTS squared. Okay, and these numbers again are all order 10 to the minus 4, 10 to the minus 5. And in fact, before the discovery of charm, this gave actually matching these calculations up gave a pretty good estimate of the charm quark mass. Okay, so this is kind of one of in the history of the discovery, early discovery of the quarks. Okay, this was an important element. Okay, now let's ask what happens in supersymmetry with all these extra. Now we have all this extra stuff. Okay, and now in particular I can write a diagram where I have S d bar. I exchange here a scalar. I have here a gaugino. So remember, I have couplings gaugino, quark, squark. Okay, so I'm using the gaugino, quark, squark coupling. I do the same thing on the other side. And what I'm using here to get this S bar D, D bar S, is some off-diagonal term. Remember, I have these mass terms, M. So I have things like this MQ squared, or I have MD bar squared. And MD bar squared is just some general matrix. It can mix the D squark and the S squark, what I call the D squark and the S squark, or what have you. And if this number isn't particularly small, if there's no suppression, then the result I get here, I don't get this Jim suppression. I get something that's order 1 over M SUSY squared, where before I had 1 over MW squared. So 1 over MW squared in my previous formula would go to 1 over M SUSY squared. And the G squared now becomes G strong squared. Okay, so that's a factor of order 10. Okay, actually, I'm sorry, to the 4th. So that factor is close to 100. And then it turns out that everything else works against you. Okay, and there's some kinematics, some kinematics and other stuff. So there's some other extra factor of 5 or so on. Okay, and so in general, this is terrible. Okay, this is many, many orders of magnitude off. If you just want to suppress this by the SUSY mass scale, you have to push the SUSY mass scale up to tens to hundreds of TeV. Okay, so this is really problematic. Unless, okay, these off-diagonal terms are small. Okay, and so what everybody does who works on supersymmetry assumes that for one reason or another that these terms are small. And in fact, the typical assumption that people will make is that these matrices, okay, so these are in general 3 by 3 matrices, and for unknown reasons, they'll assume these are some mass squared, okay, times unit matrix. And I should put approximately here because this can't be exact, because even just under a normalization group of evolution, you'll generate the off-diagonal terms. Okay, but this is a very dramatic sort of problem. It's a problem we also talked about already in the context of Technicolor and so on. And there are a variety of ways we might imagine solving that. We'll talk about them in a moment. Let me mention a couple other dramatic flavor problems. You can see better there? Yeah. Unfortunately, what the screen does is it covers the only decent blackboard in the room.
Do you need it now?
Yes. It would be nice if we could just sort of move this board out a little bit. Okay, so let me mention a couple more. So let me mention a process, another sort of dramatic process, which is mu to E gamma. Okay, so this is something, the branching ratio for mu to E gamma is now, actually I forget the numbers, but it's known to be about less than about a part in 10 to the minus 11. Okay, and it will improve. And I'm probably, maybe somebody here remembers better the numbers than me, but it will improve by a significant amount. Okay, so this is what, if it happens at all, it's very rare. And how would it happen in this framework I'm describing? Okay, well, I can have my muon comes in. Okay, the muon couple to the partner of the W, which I'll call the we know. Okay, and produce a scalar muon. The scalar muon, through these various off-diagonal terms in the matrix, in the mass matrix, can become a scalar electron. Okay, so out here can come an electron. Okay, and now again you can do an estimate, okay, of this, and you can compare this with ordinary muon decay. So ordinary muon decay, right, is something like mu to neutrino and a W, right, and an E and a nu. Okay, right, and you can compare those two, and you can see that again either this thing has to be suppressed. Okay, this thing has to be very small, or the scale again of supersymmetry breaking has to be very large to be compatible with the present limits. Okay, so this is another sort of flavor problem. It again would be solved by assuming that these mass matrices are all very nearly diagonal, very nearly proportional to the unit matrix. Okay? Okay, and let me mention one more, okay, and I'll try and just fit it in this spot. Another issue with supersymmetry, which is a very interesting one, which is CP violation. Okay. So when I counted these parameters, a lot of that counting arose because the entries in these mass matrices are complex numbers. And in a sort of general way, of course, the details depend on what exactly you're looking at, but kind of in a general way, if there are phases somewhere in your mass matrices or what have you, that will represent a violation of CP. Okay, in general, you have to check because sometimes you can redefine fields and these things disappear, but in general, you have some violation of CP. Okay, so we have all kinds of constraints on CP violation. And one of the sort of dramatic constraints arises from the neutron electric dipole moment, which is usually abbreviated DN. Okay, and the neutron electric dipole moment is extremely small. So normally, if you were just making dimensional analysis, so again in the spirit of these naturalness discussions we've had before, you would say, what's the natural value? The natural value is the electron charge times the size of the nucleus. Okay, so the size of a neutron, which is say 10 to the minus 13 centimeters. Okay, and so you'd say, well, that's about how big I would expect it to be, and the actual limits are the actual number is less than or order something, and I'm again probably not. I am probably not totally up to date, and I'm not probably remembering things well, but it's less than about 10 to the minus 25. So you have to understand in general why there's such a suppression. In the ordinary standard model, the suppression is huge. Okay, neglecting for a moment the theta angle of QCD, the suppression is huge. Okay, limit is not an issue. Okay, the reason is that you just, you sort of need to involve all three generations. You had some Feynman diagram involving all three generations. It's very highly suppressed. Okay, but in this theory, this is not the case, and we can draw a diagram that looks not so different than the one I drew here. So I can have a quark comes in. I have here a gluino and a quark. Okay, the gluino mass appears here, and one of these A terms appears here. So this is Q twiddle, and this is Q twiddle. So this could be, for example, an up or a down quark, something which will contribute to this neutron electric dipole moment. Okay, and these numbers, again, you can put in some numbers, but if the mass scale here is even a TeV, you'll see that the phases here have to be order. And now just saying things are proportional to the unit matrix isn't enough. If the phases here aren't of order apart in 100 or so, then you violate this limit. And this is also a limit this is another limit that will, like the limit here, okay, this is another limit that will improve over by sort of order of magnitude or so over the next few years. Okay? So this is interesting, and I should say it's interesting because most of the time when people try and model this or try and understand why it's small, they tend to be on the edge. Okay, so discovery or not is potentially quite interesting. Okay, so all right, so I mentioned these flavor constraints. Okay, and I'm going to talk a little bit in a few minutes about how we might deal with these, but let me just say that okay, the one way is just to ignore them and to assume, and I apologize for switching to this board, but assume that the masses are all simple, so that all the all the scalar masses at some energy scale are just some universal number, often called m0 squared, okay, and assume that the gaugino masses, again at some high scale, are some number which is often written as m1/2 and real. Okay, and so I should just maybe put an absolute value. And you'll see lots of plots which are of constraints on supersymmetric masses and so on, which are expressed. In fact, that's here. You can see it here, not so well because this didn't come out so well, but here's this, some m0 and m1/2. And these are, with a little more precision in the definition, what I'm writing here. So precision about what scale this holds and so on. But, and in fact, I guess to say a little more, this is assumed to hold at some scale, like the unification scale, and then under some renormalization group evolution, there's some splitting of the states. And so if you look, and you can't see very well in this figure, but you'll see lots of these from Maria next week, you'll see contours where these m0 and m1/2 are translated into values of squark and gaugino masses. Okay, so. All right, so this is kind of this story of soft breaking. I'm not really doing it justice. It's obviously a whole big industry, but as I say, we have these sorts of assumptions. And and basically the main alternative is something called gauge mediation, and we'll talk about that a little bit too. And basically the characteristic there is that these scalar masses, for example, are functions of the gauge quantum numbers. Okay? And that's enough to avoid these flavor problems. So rather than assuming that everything is universal, in that case, the scalar masses will be proportional to, will be functions only of gauge quantum numbers. That's enough to suppress all this flavor, all right? Because it's only states with the states that need to cancel or that might mix, okay, have the same gauge quantum numbers. And the other virtue of this structure will be we can model this pretty well. We can write down models where this arises. The main vice is that, again, I was asked this question before about what's ruled out. It's again a subject of debate, but there are people who will say that, well, at this point we've ruled out a lot of this space for gauge mediation. Okay, so we'll talk about that, I hope, a little bit more. All right, so I think that's all I want to say about flavor. I want now to come to the Higgs. Okay, and so the Higgs is sort of where the real problem of these theories arises. Okay, the real strain on supersymmetric models, and in particular on this MSSM. So in the MSSM, okay, there's if I look at the Lagrangian I wrote, okay, so this Lagrangian plus the soft breaking terms, there's a limit on the Higgs mass, an upper bound. Okay, and that upper bound says that mh squared is less than or equal to, I forget whether it, I actually don't know if it's well, it doesn't really matter. We'll put less than or equal to mz squared. Okay, So you asked if the MSSM is ruled out, and the answer is yes. Okay? So, but not quite. Okay, so first of all, where does this come from? Okay, if we think about this general theory we're writing, the supersymmetric theory with soft breakings, okay, where normally does the mass of the Higgs come from? So the mass of the Higgs, okay, mh squared, I think we saw this in Elam's talk. Mh squared is something like 2 times the quartic coupling times v squared. Okay, and this v squared, the expectation value of the Higgs, is related to mz. Okay, now the other thing, so it's related to mz, and what about lambda? Okay, so what is the quartic coupling? So in the standard model, the quartic coupling is just a parameter. Okay, and we might constrain it in various ways. I'm going to talk about that a little bit next time. Okay, we might constrain it because we don't want the couplings to blow up before we get to some high energy scale, or because we want the universe to be stable, or something else. Okay, but we don't have really much by way of constraints. But in the supersymmetric theory, we do. Okay, so where do the quartic couplings of the Higgs come from? Okay, so I've written these soft terms, but these soft terms didn't involve any quartic couplings. Okay, quartic corrections would not be soft. They would be very important at high energies. Right? They're marginal operators in the language of the renormalization group. And so those quartic couplings come from the supersymmetric terms in the action. Okay? And the only supersymmetric terms in the action for H which are quartic are the D terms. So we have this d squared for hypercharge. Okay, so let me put a g squared here. So there's some g prime squared. And we have g squared over 2 dSU2 squared. Okay, for SU2. Okay, and if you think about, remember what the d terms were, let's look at the hypercharged d term. The dy squared, so this is g prime squared over 2. The hypercharge of the Higgses is +1 or -1, but I'm using this archaic convention where the gauge coupling, where the coupling to the gauge field goes like the hypercharge divided by 2. Okay, so if I do that, then what I have, I get an extra. So I have an extra quarter, and I have HU squared minus HD squared. Is another 1/4. Okay, and then if you look at also schematically, I have g squared over 2, and again the same quarter. The quarter arising, I'll just take the Higgs to be, say 0v, and then this coupling is a quarter HU squared minus HD squared again. Okay, so roughly speaking, the quartic couplings of the Higgses are controlled by g and g prime. So it's not too surprising. Okay, so if given that this lambda is now, in fact, in a sense I'll describe in a moment, this is g squared plus g prime squared over 8. Okay, so it looks a lot like mz squared. In fact, mz squared is g squared plus g prime squared over 4 times v squared. Okay. So, so that I'll refer you to your particle physics courses or your Peskin and Schroeder chapter or something or other. Okay. So, in fact, let me take a particular limit where this formula really, I can just apply these formulas directly because I'm not good at. You guys are all probably faster with Mathematica than I am, and I'm not good at diagonal. I don't diagonalize these matrices that fast. So let me take a particular limit. Let me take a limit which is people call a decoupling limit. Okay, where mhd squared is much greater than mhu squared. Okay, so I just integrate out. I'm just going to forget about mhd squared. I'm going, we were integrating out all morning, so we integrate out mhd. Okay, so we just integrate this out. Okay, and we're left with a low energy theory which looks like some minus mu squared hu squared. Okay, and then this coupling plus g squared plus G prime squared, I'm writing the potential for the Higgs over 8 HU to the 4th. Okay? And in this case, lambda is precisely G squared plus G prime squared over 8. And we can just plug in this formula, and we see, in fact, that mh squared is mz squared. So in this limit, we have literally mh squared equals mz squared. And as I said, that's as well as we can do. Okay? Any questions about that? I feel like I saw a hand. Everyone okay? Okay, so all right. So why don't we totally give up and go home at this point, or try and modify this theory in some way? We saw this movie yesterday about LEP and the LHC, and in fact, when people were thinking about the LEP energy, one of the things they thought about is this limit, and what would be the, and one of the things LEP wanted to do was kill supersymmetry, kill the MSSM, or discover it, obviously. Okay, and so they said, okay, all we've got to do is be able to set a limit of a MZ. Okay. And then my colleague Howard Haber and John Ellis and various other people noticed not quite. And the reason is that because G squared plus G prime squared is not a very big number. So you can ask about whether are there corrections in this theory. Once you allow for supersymmetry breaking, are there corrections? Okay, and in particular, the low energy theory okay, and again, we're now all experts on integrating out. When I integrate out stuff, stuff is the technical term. When I integrate out stuff, okay, where here will mean what we're going to mean mainly is the top quark and the top squark, okay, does not have to look supersymmetric. Okay, so the very low energy theory, integrating out a lot of the supersymmetric stuff, does not have to look supersymmetric, and it can have a correction to the core decoupling. So for example, in this decoupling limit, okay, and so how does that arise? Okay, well, that'll arise because, for example, I can have here HU, a loop with this top squark. Okay, and similarly, a diagram with a top quark in it. Okay, and it's a good homework exercise, which I promise is easier, far easier than the homework exercises that you got some SPHE, to calculate these diagrams. And I recommend you calculate them as Feynman diagrams. Okay, and to show that what you get here, well, I've written it here, is, well, I haven't written it here. I've written it on the next slide, is that the change in the core decoupling is 3 yt to the 4th, the coupling to the 4th, over 16 pi squared log mt twiddle squared, the log of the top squark, divided by the top quark mass squared. Okay, so I said this is a pretty easy computation. You can see, why do you get a log? Okay, each of these diagrams is logarithmically divergent. In the limit that the squarks are degenerate with the quarks, okay, in the supersymmetric limit, they have to cancel. Because in that supersymmetric limit, this core decoupling isn't allowed. Okay, and it's easy to check that that's the case. And the coefficient, this 3, comes from the color of the squarks. Okay, it's pretty simple. It's pretty much as simple as that. The rest of the integral is totally trivial. Okay, there are finite pieces which are harder. People work harder on the finite pieces. And I've written the general formula, in fact, for the correction, a general formula for the correction to the Higgs mass. Okay, so this C2 beta is cosine of 2 beta. Beta, tangent beta is the ratio of the Higgs, the expectation value of h up to the expectation value of h down. In our decoupling limit, this is our literal decoupling limit. This is infinite. So in general, in that limit, we expect it in a realistic version of that, we expect it to be large. Okay, so anyway, so this formula, this formula in the limit of large tan beta, you can easily work out every piece of. Okay, and I don't have time here to do that for you, but I say it's not hard, and you can do more detailed computations. So in practice, people include these A terms for the A terms for the squarks and the mu term, and play around and see in what limit. And you can get up to about 140 GeV this way, because the top quark Yukawa is large. However, this is, it's sort of, if you just try and do this, for example, by making the mass of the stop very large compared to the mass of the top, okay, again, an easy limit in which to evaluate these diagrams, okay, then you find that to be compatible, say, with 125 GeV Higgs, okay, which I said was going to be my working assumption, you need stop masses of order tens of TeV. Okay, so very large, a lot larger than we really wanted to think about before. Okay, okay, so this is sort of where this issue is. So why is this a problem? Okay, so it's a problem, and I think at this point I can get rid of this finally. So why is this a problem? Okay, it's a problem from the perspective of the fine-tuning issues I raised in the beginning. Okay. So if we look at the corrections to the Higgs mass itself, so let me look at delta MHU squared. Okay, so this is given again by a Feynman diagram, by Feynman diagrams of exactly the type we studied almost in the beginning. So here might be the top, here might be the stop. Okay, so this diagram you can also evaluate easily, and you find that you get -6. We've already done this exercise, over 16 pi squared, yt squared, mt twiddle squared, and a log. Okay, so this is delta MHU squared. Okay, this is the thing. We introduced all this structure to make this correction small. So let's ask what this is. So if this is 10 TeV, so this is 10 TeV squared. I just want to make this sort of dramatic. If this is 10 TeV squared, and if this log is like log of m Planck, well, it's like m gut. So it's say it's log of 10 to the 12 or something. Okay, and we got a 2 because we're taking the square. So this is 60 or so. Yt is like 1. Okay, so we have 6 over 16 pi squared. Okay, so this thing is like, maybe it's 3 times 10 TeV squared. So this is 20 TeV all squared. It's really roughly, okay? But that's huge compared to what we're interested in with it. Right? This is much, much bigger than 125 GeV squared. Sort of the characteristic number we're interested in. Okay? So we have here a factor of tuning of a part in 10 to the 4th.
Excuse me, what do you assume for lambda here?
I took lambda the gut. Okay, now I could make different assumptions. I could put 10 to the 3 GeV or 10 to the 5 GeV, and then it would be a little better. Okay, I'm not proving anything by this statement exactly. I'm just telling you why you might be worried. Okay? And in fact, even at this scale, even if I don't worry exactly about where the Higgs mass, how the Higgs mass got so large, or I do something else, invoke some other way of getting the Higgs mass large, and I say this is 1 TeV, which is sort of typical of these limits, okay, then I still have a part of tuning of a part in 100. Okay? Now, what David said to you in his very opening lecture was 10, 100, who cares? And I'll actually argue that so give some arguments for that on Sunday, invoking exactly what he doesn't want me to talk about, which is the landscape. But still, this is what troubles people, And now there's sort of a question of, of some kind of purity or something. How much tuning bothers you? And I say, well, I'll try, and that at some level is almost a philosophical question, okay? But I'll try and give some rational basis for thinking about this on Sunday, okay? So this is the tuning, this is the origin of this tension, okay? Now, I'd like to end up here. I'm about one lecture behind. I'd like to end up here with one last thing. Okay, so where am I headed? Okay, so I think, so this was a little sort of 45-minute tour of the MSSM. Okay, there are a couple things we'd like to talk about. One is, I'd like to talk about modifying this theory. But I also want to spend at least a little time on microscopic theories of where this SUSY breaking came from. So far, I just pulled it out of my hat. And I kind of invoked the name of a tuf to allow myself that. But we'd like to understand that microscopically. In fact, one of the things I said in my introductory remarks is that supersymmetry is, actually I should ask I don't know who the authority is right now, how much time I technically have.
10 minutes.
Oh, okay, so I've got a little more time than I thought. Okay, but I know people are getting hungry, so I'll try and end on time. But I'd like to talk a little bit about microscopic supersymmetry breaking. Okay, so far, when I introduced the general supersymmetric Lagrangian yesterday, I talked then about some simple examples of models which were supersymmetric. But I didn't talk about breaking supersymmetry. Okay? So the simplest model that breaks supersymmetry, well, let me just call it, is called the O'Rafferty model. And the model looks as follows. Okay? It just has chiral fields, no gauge fields. Okay? And it has a coupling x. I guess I should put a coupling constant, some field a squared minus mu squared. So a here is a field, lambda is a coupling constant, mu is a parameter mu squared is a parameter with dimensions of mass squared, and plus some other mass parameter m a y. Okay? And let me first just show you that this model spontaneously breaks supersymmetry. Okay? So the condition for a supersymmetric vacuum, right, was that these F components, these auxiliary fields F vanish, or that the energy vanish. Okay? So this is the statement that the W d phi I should equal 0 for all the fields in the theory. And in this case, we can't satisfy this condition, because dW dx equals 0 says that lambda a squared minus mu squared equals 0, and dW dy equals 0 implies that a equals 0. Okay, so these two conditions aren't compatible. And so to figure out what happens in this theory, what you've got to do is actually write down the potential. Now, first of all, what about dW dA? The dW dA is no problem. So dW dA says that 2 lambda a x minus plus m y equals 0. And I can always just choose x and y to satisfy this. Okay, and I'll come back to this in a moment. Okay, so all right, but in any case, if I now look at the potential, I can just look at dW dx squared plus dW dy squared. Okay, this is just some polynomial. Okay, and I've only got 3.5 minutes left or something, so I won't minimize this. But you can just check that, for example, if mu squared, if lambda mu squared is much less than m squared, actually less than m squared, okay, then the minimum is at a equals y equals 0. Okay? And x, because of this, if a equals 0, x can be anything. So x is undetermined. Okay? And you're all used to this. I talked about moduli last time, and we had moduli this morning, and we had lots of moduli yesterday in Nikita's talks. Okay, so you're kind of used to that. So there's some field which isn't determined. Okay? And you can look at what the spectrum is. Okay? So for example, if x equals 0, then you can work out the spectrum. And what you find is that there are the fermions have mass m. That comes from here. Remember that the fermion mass matrix was proportional to the second derivative of W. Okay? So the second derivative terms here vanish because A and X are, I took X equals 0, so A and X are 0. Okay? And so all I get is this m here. Okay? So I have a Dirac fermion with mass m. Okay? And the scalars, well, where the scalar masses come from, well, I have to evaluate, again, this potential. And you'll find that the scalar masses have two scalars with mass m squared, m squared, and one with mass m squared plus lambda fx, the f component of x, and one with mass squared m squared minus lambda fx.
Can you explain what are exactly these fields? It's like they are scalars.
So yeah, well, okay, let's look at some of the pieces of this potential. How many seconds do I have left?
5 minutes.
Okay. I think somebody's being generous with me, but okay. So if let's look at dw dy squared, for example. dw dy squared, dw dA squared. I'm sorry, dw dA squared contains terms. Okay, so what it's got? It's got this lambda ax squared, right? So that's some quarter term where all the fields have zero expectation value. Okay, so there's a term here. All I care about, there's some dot dot plus m squared y squared. So so y is a complex field. The real and imaginary parts both have mass m squared. Okay, so that's this two scalars with mass m squared. Okay, now let's look at A. Okay, so the terms for the potential for A come from, I lost the eraser. Okay, so again, I'm sort of leaving this as a homework. View this as the outline of a homework exercise. Because you shouldn't, all these models, if they're very simple, and it's just worth playing around with these features. Okay, so if I look at the potential dw dx squared, okay, this has a piece. What does it look like? It has minus mu squared, and then it has plus lambda a squared, all squared. Okay, and then the dw dy squared. So let me put plus dw dy squared. Has a term plus m squared a squared. Okay, so just stare at this. You see I've got m squared a squared, and then I've got a cross term here with an absolute value, right? So this gives, if I assume lambda and mu are real, okay, this pushes down the mass of the real part of A and pushes up the mass of the imaginary part. Okay, so what's here? So this is the imaginary part of A. This is the real part. Okay, so supersymmetry is broken, right? The masses of all the scalars are not the same as the masses of all the fermions. Okay, you'll notice that there's a kind of interesting relation here that the sum of all the masses, the sum of the masses of the bosons squared is equal to the sum of the masses of the fermions squared. Okay, and that's actually a general relation in a certain sense. Okay, but okay, so this is a rather simple model. Okay. And the fermions are a Dirac fermion. We have a term m psi, if we look at the component Lagrangian, m psi a psi y. Right? These are two component fermions. So this is a Dirac mass. The a and the y combine to make a four component fermion. Okay? And that's so these are the four massive fermions.
But how they being derived from the superpotential?
Well, remember the rule is, well, one way is to do it directly. Okay, but if when we integrated this included a term d2w d phi I, d phi j, psi I, psi j. So it's coming from there. Okay? And it comes from the fact that the fermions each come with one theta, right? And I differentiate to get the fermion pieces. Okay? Other questions about this? Okay, so let me, since I now probably have negative 20 seconds left, let me just say what I want to do. So the one question, the first question I want to ask next time is, what happens to x? So what we have to do with here, we have to do a quantum computation of the potential for x. Okay, so again, we've been integrating out these last couple of days a lot. We're going to integrate out the massive fields, this stuff, to determine a potential for x. Okay, what about its Fermi? Then we're going to see that the potential has a minimum at x equals 0, and the field has a mass. Okay, we could ask about the scale, the fermion. The fermion is the Goldstino. The fermion is strictly massless. Okay, so this is going to be our sort of our prototype. Okay, for supersymmetry breaking. It doesn't do all we want. It's not dynamical, and we want to fix it up, so the story up, so that the breaking is dynamical. Okay, but as I say, this is going to be our prototype. So we're going to do this. We're going to develop models where the symmetry breaking is dynamical. Okay, and then in the remaining 50 seconds next week, I'll try and upset David and talk about the landscape. And give you some ways you might want to think about both extensions of the model, how we might think about the current experimental situation, and how we also might think about this naturalness question. How upset should we be by some level of fine-tuning? What kind of levels of fine-tuning might we think are reasonable? Okay, so thank you, and I hope we still get to eat lunch. Oh, question? Yes.
So you talked about the corrections in the Higgs mass. These corrections are really large. So in principle, the Higgs mass for supersymmetry for the MSSM could have arbitrary values, right?
No. No. In fact, it's interesting. So they're not large in the sense of, large relative. There's a question of large relative to what? And so there are a couple parameters in play. So it's not that the perturbation expansion is breaking down, but it is that the expansion in the top Yukawa is large compared to the gauge couplings. So those corrections are potentially important. Now, it is also true, though, that perturbation expansion isn't extremely good. So for example, what will happen if you do these computations at one loop, and you find, oh, I'm in a happy range of parameters and things don't look so tuned and so on, then unfortunately you'll go to 2 loops and you'll find the corrections aren't so small and the situation gets worse. And that's actually just the way it is. And actually you can go online, and people who are actually more skilled, younger than me and more computer literate than me can go online, and just online there's a program you can use called Fine Higgs. FEYNHIGHS, which some of you are probably familiar with. You can just ask your friends, and you just go online and you can plug in numbers, and it will output for you things like these masses and so on. Okay, and it will include the 2-loop corrections.
So this is also the reason why it's not a problem if there is no Higgs mass bound 125 GB, but maybe 800 or whatever. I'll talk more about that next time, but it's already pretty bad. I mean, people will argue. The problem with fine-tuning is it's like there's not a, where does this come from? When are you unhappy? Okay, so we don't really have, so different people are unhappy at different levels. I'll give you all kinds of reasons why you shouldn't be so unhappy, but the truth of the matter is I'm pretty unhappy. So, the real truth of the matter is we discover when there are already a zillion papers doing the MSSM and starting to do things beyond that with assuming 125 GeV Higgs. If a year from now we really have 125 GeV Higgs and it has standard model couplings and decays, then there will be a zillion more papers. And for example, this decoupling limit predicts exactly standard model stuff because when I integrate it out, I just have 1 Higgs. Okay? But maybe it's not. Maybe we'll find that the branching ratio to to two photons is 30% larger than the Standard Model predicts. That'll be real interesting. Okay, that'll tell us there's some other degrees of freedom in play. Okay, so actually, so this is one of the things to watch for, is what happens there. So the first thing to watch for with the Higgs is how close, you know, as the statistics get better, how close is the Higgs to Standard Model? My uneasy feeling is it'll be very close. If it's not, we're in, you know, that's really good from the point of view of hoping for some beyond the Standard Model physics. Then there's certainly something there. So these, you know, so a lot, at this point, we're going to know certain things soon. Within a year, well, we'll hear more, I'm sure, also from Maria, but you know, in this next round, the limits on SUSY particles are not going to get much better. They're not going to improve. The dramatic improvement will come with the higher energy runs. So again, we're going to have different developments over the next few years, which are going to, you know, hopefully give us some clues. Any other questions? Okay. We're hungry. Thank you.